Hi everyone, this is Mrs. J, and today we're going to talk about base E functions and compound interest. I have a quick warm-up for you guys, so please pause the video and give it a try. When you're ready to check your answer, you can hit play. All right, go ahead and check your work here. So I graphed this using transformations. So my parent function is just 1/3, I'll add it in, to the power of x. So this is a base 1/3 function, so it's an exponential decay. And then I found 3 coordinates from my parent function. You could use any 3 coordinates you like, and then you could transform them accordingly. So you want your graph to go to the right 6, and then you have a vertical reflection, vertical shrink, and it goes down 1. So if you transform your coordinates from your parent function, you have 3 exact coordinates, and you have a really exact graph. Remember, since your entire graph is shifting down 1, your horizontal asymptote also shifts down to y equals -1. So today we're going to talk about base E functions. So E represents an irrational number that is approximately 2.7. It's just a decimal that goes on forever. So we call this Euler's number. We could just call it E. So when we have a base E function, it looks like this. You're going to graph it like you would any other exponential function, except since your base is E, you're going to need to estimate. So we'll use 2.7 when we're getting a decimal approximation, but we can provide exact coordinates by leaving E in our coordinates. But again, we're going to graph it the same way we would any other exponential function. And since E is greater than 1, this will look like an exponential growth function. Okay, so let's give this first one a try. So again, our parent function is just e to the power of x. So we could plot a few coordinates from our parent function. So we know that all will go through 0, 1, and then we can do 1e, which again is approximately 2.7. So notice I have the exact and then the approximation. And then we can even have 2, which would be e squared. So again, e squared is the exact, and then you can get a decimal approximation for that in your calculator. It's about 7.4. So if you want, you can plot that parent function. It would look like this, approximately. So it's something like this. And our horizontal asymptote would be at y equals 0 for the parent function. And now we can transform our coordinates using f of x, what we see in f of x. So starting with our horizontal transformations, we see that we'd like to shift our graph to the right 1. So I would add 1 to all of my x values, and then we have a vertical reflection over the x-axis, vertical stretch by a factor of 2, and then our graph will shift up 6. So we can provide exact coordinates here. So this would be 1, 2, 3, and here we have 4. And then here we could just say -2e plus 6. That would be exact. And then you could plug this into your calculator to get a decimal approximation. So it's approximately 0.6. And then here we would say -2e squared plus 6. And again, you could plug that into your calculator. And we would get approximately -8.8. So again, we have the exact coordinates, but we also have the decimal approximations to help us graph. So we have, again, 1, 4. And then we have 2, 0.6. And then we would have 3, -8.8, somewhere right around here. And then also to help us, we could sketch in our horizontal asymptote, which will be at y equals 6. So it's shifted up 6. So kind of looking at what our original graph looks like and keeping in mind that we did reflect our graph, we could see that it makes sense that our graph looks something like this. And then we can look at our graph and see, well, our domain is all real numbers, our range is -infinity to 6, and our asymptote is at y equals 6. All right, now I have one for you to try on your own, so please pause the video and give it a shot. All right, go ahead and check your work here. So you can see I have my parent function coordinates, my transformed coordinates, and here I have the exact coordinates and then the decimal approximations to help me graph. So now we're going to talk about one of the main applications of exponential functions, which is the idea of compound interest. So first, I want to talk about the difference between just simple interest, which you've probably worked with before, and compound interest, which may be new to you. So simple interest is when you simply have an amount that earns interest, and that original amount is called the principal, and then you're just paid money based on the interest rate and the original amount. So if you have $125 that just earns 5% simple interest, you could see how much money you make by doing 125 times 5% as a decimal, so 0.05, and so that means that you get $6.25 in interest. So that would just be a simple interest. Here's your principal, you're paid one time 5% of that principal, so you're paid $6.25. Now, compound interest, which we're going to learn about for the rest of the lesson, is when the interest that you earn on your principal gets added to that principal, and then that new amount earns interest. So instead of earning interest on the original amount, you're earning interest on the principal plus that first interest payment. And then that new interest gets added to the original amount, and so each time you're earning interest on a larger amount because you're including the previous interest. So just to kind of visualize what's happening here, let's say you have $125, that same thing, but it earns 5% interest compounded monthly. So each month, what's going to happen is your bank is going to pay you interest. So that first month, same thing, the interest that you earn is $6.25. But this time you're going to take that $6.25 and you're going to add it into your account. So now your account has $131.25. And now when you earn 5%, you're not earning 5% off of 125, you're earning 5% of this new higher amount. So you can multiply it by 0.05 times 0.05 to see what your new interest payment. So this time you're earning about $6.56 in interest. So then you take that interest, you add it into your account. So now your account has $137.81. So the next time your bank pays you interest to the next month, again, you're not earning interest on $125 or 131.25. Now you're earning interest on the 137.81. So the interest that you earn that month would be $6.89 about. So you can see, and then that would get added. So you can see when you have a compound interest, you're not just earning interest on the principal, but you're earning interest on your interest. So your money grows faster. So there is a formula that we can use to help us work with this compound interest. So it looks like this. It's P times 1 plus R over N to the power of NT. So V is the value of the account after T years. So T is in years. And it's an account that is compounded N times per year. So N is the number of times your bank pays you interest on whatever is in your account. And P is the principal, so the starting amount, and then R is the interest rate as a decimal. So we're going to practice using this compound interest formula. So let's say a person invests $4,000 in an account that earns 3.8 annual interest. What is the value of the account after 15 years? How long would it take the value to reach $10,000? So since it's just earning 3.8% annual interest, we can assume that that means that it's just compounded annually. So it's compounded once a year. So N is equal to 1. But that money that you earn each year is then added to your account, and then you're going to earn money on that. So N is 1. We know that R is 0.038. And then T is going to be, our principal is 4,000. And then T is going to be 15 years. But just to set up the model, it would be 4,000 times 1 plus, well, since it's just R over N, which is 1, it looks like this. And since it's the power of NT, but again, N is 1, it just looks like this. And you could add the 1 and the 0.038, of course, to make it a little bit simpler. And then we can calculate the value after any number of years by just substituting T with 15. So we're finding V of 15. So it's 4,000 times 1.038 to the power of 15. And then this you could plug into your calculator. And we get approximately, if you round for money, it would be $6,998.75. So that's the value of your account after 15 years. And then they ask us, how long would it take for the value of the investment to reach $10,000? So we're wondering when this is equal to 10,000. Now, we could substitute V of t for $10,000, but then we have an exponential equation, which we're going to learn how to solve actually later in this unit. So what we can do is we can actually plug this into our graphing calculator. We're going to plug in this function. Okay. And then we're also going to graph the function y equals 10,000, which will be a constant function, a horizontal line at 10,000. And then we're going to find the point of intersection. We're going to see where this is equal to 10,000. And since they're asking how long it would take, we're going to be looking for the x value of that point of intersection. Okay, so you can see here I plugged these two into Desmos. And one thing to note, just to make it a little bit easier in terms of the scale of our graph, I set my y-axis, so I considered the money in terms of thousands. So notice instead of typing in 4,000, I typed in 4, and instead of typing in 10,000, I just typed in 10. So the y-axis is in thousands. So you could see here is my point of intersection, so it's at 24.56810. So if it says how long would it take for the value to reach 10,000, I'll take this. Well, I wouldn't want to ever round down, because at 24 years it won't have reached 10,000 yet. So I'll round up to the nearest whole year. So we'll say about 25 years. And I wouldn't want to keep it a decimal for this one, because I do know that it's simply compounded once a year, so it wouldn't reach that amount halfway through the year. So we could say about 25 years it would take for our initial investment of $4,000 to reach $10,000. And that's just it sitting there, us doing nothing to that money except letting it accrue interest. All right, let's try another one together. This one says a person invests $1,500 in an account that earns 2% interest compounded quarterly. What is the value after 10 years, and how long would it take for the investment to reach $2,000? We're going to do that part with our graphing calculator again. So we could see that our principal is, again, $1,500. The interest rate is 0.02. And then since it's compounded quarterly, that means that n is 4 because they compound it 4 times a year. So our function would be 1,500 times 1 plus 0.02 over 4 to the power of 4 times t. So first we'd like the value after 10 years. So we're finding v of t. And this we will plug into our calculator. So 4 times 10, so to the power of 40. So plug this into your calculator. And we get approximately $1,831.19. When you're plugging this into your calculator, make sure that you're plugging it in properly so your calculator knows to follow the order of operations and your calculator is doing what you actually want it to do. Now to see how long it would take the value of the investment to reach $2,000, again, I can do this with my graphing calculator by graphing my function that represents the value and then also graphing the function y equals 2,000 and seeing where those two graphs intersect. And again, since they're asking how long would it take, we're looking for the x value of that intersection. So I'm going to go plug that into Desmos. All right, so here's my two graphs. And again, just to make the scale a little more manageable, the y-axis is now scaled by hundreds. So you could say I have 15 instead of 1,500 and 20 instead of 2,000. So you could see here that they intersect at this coordinate. And we would take the x value of that coordinate. Now, since it is compounded quarterly, I could actually round this to the nearest quarter. So I wouldn't round down. Again, I'd always round up to make sure that I've made that money. So we could actually say about 14 and a half years. And of course, in terms of the rounding, the directions here weren't specific. So look for the directions first, and then if there aren't any, you can kind of use your best judgment on how to round. All right, so at this point, I'm going to ask you to pause the video and give this one a try on your own. And when you're ready, you can check your answers. All right, go ahead and check your work here. If it's compounded semi-annually, that means that it's compounded twice a year. So you see the value of the account after 8 years is a little over $981, and it would take approximately 15 years for the value to reach 1,500. You can see the scale of my y-axis here is in hundreds. Again, I took this and I rounded up to make sure, we wouldn't want to round down because you wouldn't have reached that money yet. So you will always round up to the nearest interval. So you might have gathered from the previous examples that the more often you compound something, the more money you're going to make because you're earning interest on your interest more often. Now, an account could be compounded quarterly, it could be compounded monthly, weekly, daily, which would be, it's kind of rare, but you might even sometimes see a scenario where something is compounded continuously. So imagine like every fraction of a second of every single day, you're constantly earning interest on your previous amount. So it's being compounded continuously. Anytime you have this continuous growth, we're actually going to model it with a base E function. So for this, the way that the formula that we can use for a continuously compounded interest is V of t equals P times E to the power of RT. So slightly different than our other compound interest formula. But P is still the principal, R is the interest rate as a decimal, T is the number of years, and it's just going to be a base E. So anytime you have continuous growth, that is going to be modeled with a base E exponential function. So here it says a person invests $5,500 in an account that earns 2.7 annual interest compounded continuously. What is the value of the account after 15 years, and how long would it take for it to reach $1,200? So we know that the principal is $5,500, The interest rate as a decimal is 0.027. And so we can make our model. So 5,500 times e to the power of 0.027 t. So to see how much our account is worth after 15 years, we can just substitute t with 15. Make sure when you're plugging this into your calculator that this is typed in appropriately. So let's get our decimal approximation. So our account would be worth approximately $8,246.16 after 15 years. Then to see how long it would take for it to reach $1,200. Well, actually here, I'm sorry guys, I meant for this to say $12,000. We can plug in these two functions into our graphing calculator and see their point of intersection. So I have the graph from Desmos. Looks like this. So you can see again that my y-axis, I scaled it to the thousands just to make the numbers a little more manageable. And you can see here's my point of intersection. So for this one, again, it's not really clear what to round to, but since it's being compounded continuously, I don't know, I'll round it to 28.9 years. All right, so here's the last example for you to try. So please pause the video and hit play when you're ready to check. All right, go ahead and check your work here. So you can see my n value is changing for each one. So your n equals 1, n equals 2, 4, 12, 52, 365. And then here we have our continuous growth model. So you can see that the more it's compounded, more often it's compounded, the more you'll earn. Initially, the jump is much bigger, and you can see like the difference between daily and continuous is not huge. It's like about $2. But again, the generalization you can make here is the more often it's compounded, the more money you will make. All right, so that is all for today's video. Thank you so much for watching.